In this section, we're going to talk about two simple but important structures. We're going to talk about the equations of lines and the equations of planes. Okay, let's start with lines. Now, you know lines. You've dealt with lines before, right? How do we write the equation of a line? For most people, the equation they know best is y equals mx plus b. Okay, this describes the equation of a line with slope m and y-intercept 0, comma b. But there's a trick to this. This only works in 2D. If you try to use the same kind of equation in 3D, you will not get a line. You'll actually get a plane. And we'll talk about those a little bit later. Okay? But lines are so important. We want to be able to express the equation of a line in any number of dimensions very easily. So we need to somehow adapt this idea so that we can express the equations of lines in 3 dimensions or even 4 dimensions or 5 dimensions if we wanted to. Okay? So what we're going to do this, we're going to use our knowledge of vectors to describe the equation of a line. All right? So I'm going to draw everything in 2D to begin with. We already have a great way to describe lines in 2D. We want to find a way to describe lines using vectors, though, so that we could use it in 3D and higher dimensions if we wanted to. I'm going to just draw the pictures in 2D because it's much easier to draw in 2 dimensions. But just know that the ideas that we will develop will also work for higher dimensions because we are going to develop them using vectors. And vectors work in any number of dimensions. All right? So we're going to start off with a simple case. We're going to consider a line that passes through the origin. In a little bit, we will extend our ideas to lines that pass through other points, that don't pass through the origin. All right? So how can we describe the equation of this line using vectors? Okay, so in a way that we'll be able to extend to higher dimensions. Well, let's draw a vector in standard position, so with its tail at the origin, and that is parallel to the line. So it points in the same direction as the line. Okay, I'm going to call this V. Notice that we actually have a vector operation that can already allows us to describe every point on this line. Once I get that vector, all I need to do is scale that vector, and I could describe any point on this line, right? If I take that vector and multiply by 2, so it's twice as long, I can get to that point, right? If I wanted to get to this point, I just take that vector, that direction vector, and I go half as long. I go to there. Gets me to that point. If I want to go backwards, just multiply that direction vector by a negative scalar, and it will point this direction to that point. So once I have a direction vector, any direction vector, I can get to any point on this line just by scaling that vector. All right? So the equation that we're going to use for a line positioned at the origin is just that direction vector, and then I'm going to scale it. And what I want to do is I want to be allowed to change the scalar. So the direction vector here, in stone, concrete, won't move. Okay? But I want to be allowed to scale the vector. The scalar is going to be my variable. Okay? I'm going to call that variable t. This is a function, which I will call r of t. It's a vector valued function because it spits out a vector. And it will describe this line. It can reach every point on that line by just choosing different values for the scalar t, right? So let's summarize. a line through the origin can be described by the equation r of t equals tv, where v is a vector parallel to the line. Okay. When we put that vector at the origin, or if we put that vector on the line, it actually looks like it's part of the line, right? But because vectors don't, strictly speaking, have position, we can move it wherever we want. So we're imagining we move it on the line with its tail at the origin. So the output of this will be a point on the line. This variable here, notice it's not one of the variables we're used to, right? We have an x-axis, we have a y-axis, x and y. Where the heck did t come from? So t is an additional variable that is convenient for describing equations, describing graphs in vector form. We call it a parameter. We give this variable special name parameter. Graphically, you can think about it as a time variable. Okay, in a real life situation, we could think about that as a time variable, and I will show you what that would be like, all right, later on. But even when time isn't relevant to the application, it is still a useful variable to help us describe what's going on. Okay. And t is, and we call this variable, this additional variable, a parameter. Okay. Notice there's nothing special about v other than the fact that it is parallel to the line, that it points in the same direction as the line. There are lots of vectors that I could choose that could do that, right? So I have v here, but I could also choose this vector here. Give it another name. Let's call it u. It's also a vector parallel to the line. It's pointing the exact opposite direction. That's okay. We can also use that vector to describe the equation of this line. So let me give it a different name. This one I called r. Let's call this one q. So this function I'll name q, and I'll even give it a different parameter. Okay, so s is the variable I plug in. U is a concrete vector I've already chosen, right? This will also get to every point on the line. If I choose different values for s, different scalars, then I will stretch out u differently, okay? Notice that if I plug in a value for t here and a value for s here, if it's the same value, say I plug in 2, I will get 2 different values on the line, 2 different points on the line. Right? So 2v, I end up getting that point, whereas 2u, I end up getting something like this point. Totally different point. All right? So I could plug in the same thing into both these functions, but get totally different points out. But both points are on the line. Okay? Notice then that the equation of a line in this form is not unique. Both of these are valid equations of the line. Totally different equations. Plug in different things, you get different values out. Okay? They're both give me all the points on the line. Compare that to y equals mx plus b. in 2 dimensions, this is essentially unique. If you have an equation of the line, you put it in y equals mx plus b form, there's really only way it goes in y equals mx plus b form. It is unique in that sense. The method we're developing now, this works in any number of dimensions, but it is not unique. So I've drawn the picture in 2 dimensions. But this same equation, these same equations would hold in 3 dimensions. If you have a vector parallel to your line, and your line goes through the origin, then this will describe all points along that line. This also would describe all points along that line in 3 dimensions. Okay? Okay. So far, we have the equation of the line, but only when the line goes through the origin. We need to be able to talk about the equation of the line when it doesn't go through the origin. Okay, so how do we deal with that? So let's draw another picture here. We've got a line here that definitely does not go through the origin. How do we describe the equation of this line? So let's say we have a point on this line. We do know some point on this line. Not the origin, but some other point. Let's call it x naught, y naught. Okay? And just as before, we have a vector parallel to the line. Vector v. Now, if I scale vector v, it's still going to go up and down the line, right? If I go twice v, I go here. If I go negative half v, I'll go this way, right? But with no additional information and interpreting the output as a point, we would interpret v as being in standard position. So if we scale it, we would actually get this line here through the origin. Okay? And that's not what we want. We want to go through this line up here. So how do I do that? Well, the trick is I first have to move to a point on the line. So before I move in the direction of the line, I first have to move to the line. Okay, and I can move to the line by traversing a vector that starts at the origin and ends at this point. Okay, and that would be the vector, since the vector is pointing to the point x naught, y naught, it is the vector x naught, y naught. Okay, and so the equation of a line not centered at the origin, you just have to get to a point on the line first. So in 2 dimensions, maybe we go to x naught, y naught. Okay, that gets us to the point on the line. And then once I'm on the line, then I can stretch my direction vector back and forth. So then I go t times that direction vector. All right, notice this is vector addition. And if you think about it, it makes sense. Okay, if I plug in 2t for, or just 2 4t, I get 2v. So what do I do first? I traverse this vector to get on the line. And then once I'm on the line, then I would add 2 times v. So that gets me to here, to this point. If we draw the picture for vector addition, complete the triangle, the vector would point from the origin, from where I start, to where I end up after I add all those vectors together, after I traverse all those vectors. Points to the same point. Okay? Point on the line. Now I've drawn this picture again in 2 dimensions. The same idea works in any number of dimensions. The equation of a line passing through the point let's give it a name. Let's call it R naught, right? So here R naught would be X naught, Y naught. In 3 dimensions, you'd throw in a Z naught usually, right? But it is a particular point on the line. So the equation of a line passing through the point R naught and parallel to vector V is given by R of t equals, first get to a point on the line, and then once you're on the line, then you can move up and down the line in the direction of the line by scaling that direction vector. Okay, so this point on the line and vector v here is a direction vector, a vector parallel to the line. And I want to emphasize once again that the equation of a line written in this form is not unique. Because there are lots of points on the line. I could choose any one of them and I will still get an equation for the line. Okay? There's no preferred point. I could use any point on the line. What about the direction vector? There are lots of vectors parallel to the line. I could use any vector parallel to the line. I will still get an equation for the line. So there are lots of choices here. There isn't one unique equation. But this formula for the equation of a line works in any number of dimensions. It works in 2 dimensions. It works in 3 dimensions. It works in 104 dimensions. Because we're using vectors, and vectors work in any number of dimensions. All right, let's put what we just learned to practice. Let's do an example. We want to find the equation of the line passing through 2 points A and B. Now we're going to stay in 2 dimensions because I want to really help you see what it is we're dealing with. And again, it's easier to draw this in 2 dimensions, but I just want to emphasize one more time. The same strategy will work if I want to find the equation of a line passing through 2 points in 3 dimensions, or for that matter, in 7 dimensions, right? Any number of dimensions. This strategy works, all right? So let's draw a quick picture of where we're at. We have 2 points. We have point A, which is at 1, 3, right there. That's A. And point B is at 3, 2. So that'd be there. Okay. So if I want to find the equation of a line passing through these 2 points, and I'm going to use the vector form of an equation. That's what we're learning, of course, right? I need a point on the line and a vector parallel to the line. Point on the line, vector parallel to the line. Now, do I have a point on the line? Yeah, in fact, I have 2, right? I want my line to be this line here that goes through both of these points. Okay? So I already have 2 points on the line. I have point A and point B. So which one do I use? Doesn't matter. Okay, either point will work. In fact, if I wanted to, I could calculate a 3rd point down here somewhere. That point would also work. Any point on the line will work. Okay? And I have 2 of them already. I don't have to do any further calculation there. Now I need a vector parallel to the line. Okay? Easiest way to do that would be to find the vector pointing from one point to another. So I could either find the vector pointing from A to B, or find the vector pointing from B to A. Again, we have choices here, and they are all good. As long as I have a vector parallel to the line, I will get the correct equation of a line when I'm done. Okay? So let's do go in this direction. Okay, let's take the vector from A to B. We'll call this vector V. So vector V is my direction vector. And it will be the vector pointing from A to B. So I just want n minus start. So I end up at B. That's 0.32. I subtract the point I start off from. That's point A, 1, 3. If I subtract them, I get 3 minus 1, that's 2. And 2 minus 3, that's negative 1. Okay, we have our direction vector. And so the equation of our line, put it all together. I need a point on the line. Again, I could use either one of these. Doesn't matter. I'll use the first one. I'll use point A. I get 1, 3 plus variable t times my direction vector, which I just calculated as 2, negative 1. And that's my final answer. For different values of t that I plug in, I will get different points on this line. And that's what I'm looking for. Okay? If I wanted to, I could shove this all together, do the scalar multiplication. So if I multiply the t through, I get 2t, and then negative 1 times t is negative t. And then add the vectors together. I have 1 plus 2t, and I have 3 minus t. This is exactly the same thing. Okay? I kind of like this form a little better because it's real easy to grab the important details. Oh, that's the point of the line. Oh, that's the vector parallel to the line. But it's also easy to deconstruct if you're given something like this, because the guys without t's, well, there would be the components of the point parallel to the line. I'm sorry, the components of the point on the line. The terms with the t's, well, put them together and then pull out the t, you get the vector parallel to the line. So even when it's in this form, it's real easy to see the point on the line and find a vector parallel to the line. So we now know that the equation of a line we can express this way. R of t equals R naught plus t times v. And this is how we express the equation of a line in vector form. This is my favorite way to express the equation of a line. But it's not the only way. And sometimes we see the equation of a line like this expressed in a different form called parametric form, where we break down each component in the equation. All right. So to do this, we need to make certain what dimension we're going to be in. So let's, for this example, let's say we're in R3. Okay. Let me write it down here. The same principles that I'm about to do apply to R2, or for that matter, R4. But let's say we're in three-dimensional space for now. The output of this function, the R of t, is going to be a three-dimensional vector, right? A three-dimensional vector that points from the origin to a point. So I can rewrite this R of t. Notice it's got the arrow above it, indicating it is a vector. I can write it as a vector with, in this case, 3 components. You could almost think of this as 3 separate functions: x of t, y of t, z of t. Okay? And on this side, I could think of R naught. This is just the a point on the line. So it's just the x, y, and z components of that point. Plus t is a scalar, and then v is the direction vector, which I will label a, b, c. Okay, so if we do the vector addition on the right-hand side, and the scalar multiplication. My first component would be x naught plus t times a. Actually, let me flip those around. A times t, because a is not a vector, so we usually write the variable second when you have a scalar times a variable. Y naught plus b times t, and the last component is z naught plus c times t. And that's all equal to x of t, y of t, z of t. Okay? This is exactly the same information that's contained here, but now we're being real careful to emphasize the different components. And in fact, we can equate the components on each side. And that's what we do to get this in parametric form. So x of t, the first component here, will just be the same as the first component here. They're equal, right? So that's x naught plus at. Y of t, second component on the left side, is equal to the second component on the right side, y naught plus bt. Third component on the left side, z of t, is equal to the third component on the right side, z naught plus ct. This contains exactly the same information, but it's written with an emphasis on the different components. We call this this form parametric form. Parametric as in parameter. We have that parameter still. And again, it emphasizes exactly the same information. I can look at this and say, okay, the values without a t, that would be the components of the point that lies on the line. So point on line, x naught, y naught, z naught. And then the direction vector would be the coefficients of the variable t, the coefficients of the parameter. So it's another way to express the same information that we express up here. Let's take a look at this example with parametric equations. So we want to consider this line defined by the parametric equations. We want to find a vector parallel to the line and a point that lies on the line. Okay, so I look at this and I can immediately recognize a point that lies on the line and a vector parallel to the line. So for the point that lies on the line, I want the numbers that aren't being multiplied by t. So for this first equation, it's 1. For the last equation, it's -1. For the y equation, the middle equation, there is no number not being multiplied by t. In that case, I imagine it's a 0, right? There's an invisible 0 there. So the point on the line well, in the x equation, we have a 1. In the y equation, we have a 0. In the z equation, we have a -1. If we want a vector parallel to the line, we just take the coefficients of the parameter t. So -7, 5, -10. And those are the two pieces of information that we need to be able to graph a line. We know the point on the line. We know which direction we're going once we get there. Okay. So again, this is in parametric form. If you want to put it back into vector form, that's easy. Okay. My three equations are x of t, y of t, z of t. X of t is equal to 1 minus 7t. Y of t is equal to 5t, and z of t is -1 minus 10t. And now on the right-hand side of this equation, I'm going to separate this into two vectors. one with the terms with t in it and one with the terms without t in it. So without t, I have a 1 in the first component. I don't have anything without a t in the second component. And I have a -1 in the third component. Okay, and then with t, -17 in the first component, 5t in the second component, and -10t in the third component. These two are exactly the same, right? I've just broken this up into two vectors that are being added together instead of one big vector. And then because I separated this so that only components with t's are in this vector, I can factor out t here as a scalar multiple. So I leave the first vector unchanged. And in the second vector, I'm going to factor out the common scalar multiple t. Okay, and now we have the equation of the line in vector form. It's exactly the same. It tells me the same information. Point on the line, the vector without the t in front, and the vector with the t in front tells me the direction vector. That's exactly the same information that I already had. Okay. Now, just to clarify, this problem did not ask me to do this part, but I want to make sure you understand that whether we're writing the equation of the line in parametric form or in vector form, it's the exact same information that we are communicating. I wanted to give you a little more intuition about how we can think about this parameter in the equation of a line. Okay, so I have here the equation of a line. It's in vector form. Okay, you can see it right here. So it's vector 1, 1 plus t times the vector 2, 1. So 2, 1 is the direction vector. 1, 1 is the point on the line. Okay. So what we're going to do is we're going to see what happens to a point as we increase the scalar value that we're plugging in. So I'm allowing it to be a here, and I'm going to change that a. Right, so right here I'm going to change the a. So you could see what the value is when a is 0. We're at the 0.11. Makes sense. That's the initial point. Okay. And what happens when I change a? So this is going to gradually change a. Okay. And then it just resets. So it plugs in negative values and then positive values. Okay. So what you see as a changes is almost an animation. And often we will use parametric equations this way. We could talk about maybe the motion of a particle in physics, for example. Okay. Now, the way we're describing it here, that particle would be going in a straight line with a constant velocity. Okay. But there are other ways a particle can go along that straight line, right? So let's take it back to 0, back to its initial position. So this equation also describes the same line. I have a different initial point, and my direction vector here, notice it's half of the direction vector I'm using in the other equation, okay? But it describes the same line. So here's the initial point on this line. You could see the initial point here is at -1, 0. What do you think is going to happen when I press that play button? Let's find out. Let's compare that orange point to the blue point. Okay. Notice they are both moving along the line. Their motion describes the same line, but they have different starting points and they have different speeds along that line. Okay. In this case, this speed, because I used half of the original direction vector, it's moving half as fast. Okay. What happens if I use a negative vector? All I'm doing is I'm flipping the direction of the vector, and so it's still parallel to the line. It's still a direction vector for the line, but now it's pointing the other direction. What's going to happen? Now I'm changing the direction of motion. Okay, see how that orange ball, that orange dot is going in the other direction? It describes the same line, but its position at a given point in time and how fast it's moving is different for the two different dots. And so we could describe two different particles in space going along the same trajectory, but just moving at different speeds, having different positions at the same time. Okay? For this example, we want to determine if two lines intersect. And if they do, we want to find the point of intersection. Now, I want to emphasize that these are lines that live in three-dimensional space, right? And so the possible ways that lines can relate to each other in three-dimensional space are a little bit different than in two-dimensional space. In 2D, I could have two lines intersect at a point, right? Or I could have two lines be parallel. Or the two lines could really be the same line, right? They're just kind of in disguise and we didn't realize that they're the same line right away. But we could really have an equation describing the same line, okay? Now, all of these things are also possible in 3 dimensions, but we also get an extra, okay? In 3 dimensions, we could also have none of these things happen. We could have one line one way, and then because we have an extra dimension, we could have another line that passes, so it doesn't intersect, maybe it passes below it, and going in a completely different direction. Don't touch it all, okay? We call these skew lines. Okay? So we want to determine if these intersect. If they intersect, we want to find the point of intersection. If they don't, it'd be nice to know if they are parallel or if they're skew. Okay? It's actually easiest to test if they are parallel or the same line first. This case is the easiest to test because all we have to do is to see if they have if their direction vectors are scalar multiples of each other. If they're pointing the same direction, which is what they would be doing if they are parallel or if they're the same line, if they're pointing the same direction, then their direction vectors are going to be scalar multiples of each other. Okay? So let's start by testing if these two vectors are scalar multiples of each other, if these two lines are scalar multiples of each other. And let's start with a clean page here. Okay. So parallel or the same line. Well, if they are, then this direction vector, and I know this is the direction vector because it's the one being multiplied by the parameter. So that first direction vector, 3, 2, negative 3, would be a scalar multiple of the direction vector of the other line, the one multiplying the other parameter, 1, negative 2, 0. That's multiplied by a scalar, 1, negative 2, 0. So I want to see if this has a solution. Now, if I break this down component-wise, I actually get a system of equations. Okay, so the first equation, first component on the left equals first component on the right. If this has an equation, I can, or if this has a solution, I can already see k is going to have to be 3. Okay, let's look at the second component. I get 2 on the left and negative 2k on the right. And the third component is negative 3 on the left, and on the right, it's 0k. And I could see right away, this is no solution, right? And that's why I usually test whether two lines are parallel or the same first, because it's real easy to test, okay? This k would have to be 3. There is no k that would ever make this one work. And even if I could, this one also doesn't work, right? We would need k to solve all 3 of these equations at the same time. And there is no 1k that could solve all three of these equations. So is it parallel or the same line? No, because their direction vectors are not parallel. They're not just scalar multiples of each other. Okay? So if they're not parallel and they're not the same line, that means they either intersect or they are skew. So let's test that next. Do they intersect? Okay. Again, let's get a fresh page because I want to be able to see those equations. So intersect next. If they're not parallel and they don't intersect, then they must be skew. Okay, so we're going to test intersection. If they intersect, there is a point which they share. But we got to be careful here because they may not reach the same point at the same time. Okay, this equation tells me the points that we reach with this line. This equation tells me the points we reach with that line. If we reach the same point at the same time, then for some value of t and for some value of s, these two equations are going to be the same. Okay, so for some value of t, 3, 2, negative 3, t plus 0, negative 2, negative 4 equals the second line for some value of s. S plus 3, 8, negative 10. There we go. Okay, so if this equation has a solution, then they intersect. If there is an S and a T, that makes this equation true, the lines intersect. If there is no S and T that makes this equation true, if they do not intersect, then we've already checked if they're parallel or equal, and we said no. Okay, that was the first thing we checked. So they're not parallel or equal. If they don't intersect, then the only remaining possibility is the two lines must be skew. They don't intersect, they're not parallel, they just go in completely different directions. Okay? Okay. So what I'm going to do is I'm going to break this down into a system of equations. Okay, and to do that, I'm going to do the scalar multiplication and vector addition on both sides first. So on the left side, I get 3t, comma, 2t minus 2, comma, negative 3t minus 4. Okay, just scalar multiplying the t in and then adding the vectors together. Same thing on the right-hand side. I get 1s plus 3, negative 2s plus 8, and 0s plus negative 10. Okay? And now that I have broken down both the left and the right side into vectors, the only way these two vectors are equal if their corresponding components are equal. Okay, so first component equals first component. Second component equals second component. Third component equals third component. And I get a system of equations in two variables. Notice there are three equations to this system, which means if this solution has if this system has a solution, we say the system is overdetermined. Even if it doesn't, we say the system's overdetermined. If we have more equations and we have variables, then it gets a little bit trickier to make sure we have a unique solution here. All right? Okay. The first thing I noticed for this particular system, I've got an equation with only one variable. That's going to make it a lot easier. Okay? Normally what I would do is I'd pick two equations, and then I'd use elimination to eliminate one of the variables. But in this case, since I've got one equation with only one variable in it, I can easily solve this one equation for that one variable. Okay, so let's start by doing that. I get negative 3t. I'm going to add the 4 to the other side. I get negative 6. If I divide both sides by negative 3, t is going to be 2. So in order to make this work, this equation requires that t equals 2. Okay, now I can plug that t equals 2 into one of the other equations, doesn't matter which one, figure out what S would have to be. All right, let's take that and plug it back in here. So I get 3 times 2 equals S plus 3. So 6 equals S plus 3. If I subtract 3 from both sides, I find that S is 3. Okay, so I've got an S, I've got a T. Does that mean I have a solution to the system of equations? Not necessarily. This S and this T make this equation and this equation true. But those are the only two equations I've used so far. And I would need to make sure all the equations in the system are true. So now that I've got S and T, I need to plug it in here to make sure that this equation works with that S and T that already works for the other two equations. Okay? So let's plug in the S and T. So 2 times the T that I already found, 2 minus 2. I want to check if this is equal to negative 2 times the S I already found, which is 3, plus 8. 2 times 2 is 4, minus 2 on the left side. You know what? Let's just do it. We're in Calculus 3. We could do it all at once. 2 times 2 is 4, minus 2 is 2. Left side, on the right side, negative 2 times 3 is negative 6, plus 8 is 2. Hey, 2 equals 2. That's what we wanted to see. It checks out. So that S and that T work all the time, which means that the two lines do intersect. Notice, though, that we haven't found the point of intersection yet. We found S and T. Those are the parameters. They don't tell me immediately what the point is. They tell me the value I need to plug in to get the point. Okay, they need to tell me at what time these two lines cross. If we think about this as a particle in motion, as a particle moving along the line. Okay, then for the first line, the particle gets to the point of intersection at time t. For the second line, if we think about that line as the motion of a particle, that particle gets to the point of intersection at time s equals 3. Okay, so to find the point of intersection, I either need to plug the value of t I found into L1, or I need to plug in the value of s I found into L2. And if I've done the math right, they should give me the same answer, so I only need to do it for one. Okay, so let's plug in the t. T equals 2 into line 1. So line 1 was, let me just grab it so I don't have to look back. So I'm going to plug in t equals 2. I get 3 to negative 3, plug in the 2 for the t, plus 0, negative 2, negative 4. 3 times 2 is 6. 2 times 2 is 4. Negative 3 times 2 is negative 6. Just doing the scalar multiplication right here. And on the right side here, that stays the same. And then just add the two vectors together. I get 6 plus 0 is 6. 4 plus negative 2 is 2. And negative 6 plus negative 4 is negative 10. And so the two lines will intersect. They hit the same point at 6 to negative 10. That is the point that they have in common. Right? And if you wanted to really check your work, take s equals 3 and plug it into the second equation. You will find that you get the exact same point. In this example, we want to find the acute angle between two intersecting lines. So we're already told the lines intersect. We don't have to test that. When we have two intersecting lines, they'll form an angle, right? They'll actually form two. They'll form one angle here and one angle here. An acute angle is an angle that is less than 90 degrees, right? So we want the smaller of the two angles. Okay. So how are we going to do this? Turns out this is fairly straightforward using vector math. Both these lines rather, have a direction vector. It's the vector that is being multiplied by the parameter. Okay, so if we kind of imagine those vectors, those direction vectors being placed at the point of intersection, then what we could do is, instead of finding the angle between the two lines, we could find the angle between the two direction vectors. And that will also be the angle between the two lines. Okay, how do we find an angle between two vectors? Well, we have a couple methods, don't we? For two vectors, and let's call them V and W. So the dot product between V and W, remember, is norm of V, norm of W cosine theta. And so that's one way to get at that angle. The other way is the norm of the cross product of two vectors is equal to the product of the norms of the two vectors times sine of the angle between them. Okay? Most of the time we use this one. Dot product's easier to take than a cross product. Okay, and that's what we'll do here. All right, so I'm going to do this with the two direction vectors right here. Notice I'm not going to use these guys at all. Okay, I don't care about the positions of the lines at all. All I care is what direction are they going in. Since I already know they're intersecting, the problem tells me that. I don't have to test it, and I can assume they're intersecting, and I just have to worry about the directions the lines are in. Okay? All right. So we'll let this first guy, we'll let that be V. So V will be the direction vector for our first line, -4, 3, 1. And vector W, I'll make that the direction vector for our second line. That's -5, 5, 2. Okay? So for this, I'm going to need the dot product of the two vectors. I'm also going to need the norms of each of the vectors. Okay? So let's take the dot product. V dot W is multiply corresponding components. -4 times -5 is 20. 3 times 5 is 15. 1 times 2 is 2. Add them all together. 20 plus 15 is 35 plus 2 is 37. So the dot product gives me 37. And then take the norms of both V and W. Norm of V is first component squared plus second component squared plus third component squared. I get 16 plus 9 is 25 plus 1 is 26. Square root of 26. And norm of W is square root of first component squared plus second component squared plus third component squared. That's going to give me 25 plus 25 is 50 plus 4 is 54. Okay? So plug them into this formula here. The dot product was 37, so that goes on the left side. So 37 is going to be equal to the norm of V. That was square root of 26. Times the norm of W. That's square root of 54. Times cosine of the angle between them. Okay? And so if I isolate the cosine theta, I get 37 over root 26 times root 54. That's cosine theta. And then I want to uncosine it, so take the arc cosine. And that will give me the angle I want. Okay, and now it's calculator work. So let's pull in the calculator. Okay, I am in degrees. I want to be in degrees. The original problem, if I show you the original problem, it asks that the angle be in degrees, right? So we want to make sure that we are in degrees. And I'm going to get arc cosine of 37 divided by square root of 26 times square root of 54. You can put both these square roots under the same root if you want. Save you typing a root. It's the same thing. Okay. And so I am in degrees, and I get 9.084. Okay. So, in fact, let me copy down the whole thing. I'm not a big fan of rounding when you can avoid it. 9.084357776 degrees is my theta. Okay, that is the angle. Remember, I do want the acute angle. Okay, and as I explained at the beginning, there are two possibilities that I could get. I could get this guy, or I could get this guy. In this case, I've already gotten the acute angle. The acute angle is the angle that's less than 90 degrees. If I had gotten this angle instead of this was the theta I got, then the angle that I want, the acute angle, plus the angle that I get, theta, would be 180 degrees. So I could find the angle I want by taking 180 degrees minus the angle that I got. Okay. Again, this time, I already have an angle that's less than 90 degrees, so that's what I want. And so I'm done. That's my answer. That is the angle of intersection between the two lines. In this example, we want to find the distance from a point to a line. So the first question we got to ask ourselves is, what do we even mean by the distance from a point to a line? Okay, so we have a line, we have some point up here. Let's call this point P, right? There are lots of ways to measure the distance from this point to this line, right? There are lots of ways we could get there. So which one of these is the distance? Okay. Well, when we're measuring distance, the rule of thumb is we take the shortest distance. That's what we mean by distance, the shortest path. All right. So in this case, the shortest path would be going directly to the line. And the path here that we take from the point to the line would be orthogonal to the line. It'd meet it at a 90-degree angle. All right. So how do we go about measuring this? Well, we know the point we're interested in. We know this point. And we know a couple things about the line, right? We know a point on the line. Okay. In this case, that would be this point. From the equation of the line, we know there's a point on the line. And we know a vector parallel to the line. That would be this vector in this particular instance. Okay? So what we're going to do is we're going to think about the vector from R naught to P. Why that? Well, ideally we would want the vector from this point to P, right? But I have no idea where on the line this point lives. Okay? And since I can't find this point, I'm going to, I'm going to do the next best thing. I'm going to take a random point. This point's easy to find. Okay? So I'm going to take the distance from this point that lives on the line to this point where I want to measure the distance from the line to this point. Okay? And the vector I get, n minus start, I get P minus R naught. All right. And now, drawing this as a triangle, this is starting to look familiar, right? Because we know that we could think about these as components of this vector here. And we know we can measure these components using the dot product and the cross product. Okay. In particular, if we think about the angle between the vector p minus r naught and between vector v, then we can use trigonometry to get the length of this side here. Let's call this d for distance. Okay, we could get the length, the distance from the point to the line. So using trigonometry, we know sine of theta is equal to opposite d, the length from the point to the line, over hypotenuse, which would be the length of vector p minus r naught. So I'll take the magnitude, I'll take the norm. Okay. And what else do we know about sine theta? We also know that the cross product between v and p minus r naught, in fact, let's do it. If I take the cross product between v and p minus r naught, then what do I get? I get norm of v, norm of the vector p minus r naught times sine of theta. Okay, so if I want d, and if I rearrange this, I can find d, right? Norm of p minus r naught sine of theta equals d, then all I've got to do is divide. So this is d. That's what I want. Okay, so let's just divide by norm of v, and I have a formula for d. So v cross p minus r naught, norm of that, over norm of v. Equals p minus r naught sine of theta, which is the distance I'm looking for. Okay, so this is what I'm going to do. That's my strategy. And I got there using some simple vector math. All right. I do want to point out, notice I'm dividing by the norm of v. I'm not actually going to write it down, but I could move that scalar into this norm and then multiply it by this v. What it's effectively doing is it's normalizing vector v. It's turning it into a unit vector, a vector of length 1. Remember, we think of unit vectors as vectors where we care about direction but not its length. And that's exactly what we think about here. We really don't care how long this vector is. We're only using it because it's a vector parallel to the line. We care about its direction. It's pointing in the direction of the line. We don't care how long it is. And that's why we turn it into a unit vector. Okay? So, we shouldn't be surprised that we see that. Okay. So we know our strategy now. Let's plug in our actual points and do it for this particular problem. Okay? So point P would be 985. Vector V is 1, -5, -2, and R naught is 4, -2, 3. So point P as a vector, 985. Now I've talked about this before, but notice I'm converting the point to a vector. Points and vectors technically aren't the same thing, but I could always think of any point. I can rethink about it as the vector pointing from the origin to that point. Okay? And often it's more convenient to think about that way. So this would be the vector pointing from the origin to this point. Okay, vector v is the direction vector of the line. That'd be this guy right here. 1, -5, -2. and R naught is a point on the line. Really, any point on the line will do, but this one is awfully easy to find, right? 4, -2, 3. Okay, and that gives me everything I need to find the distance d. I just need to plug into this formula that we found together. All right. So on top, I'm first going to need to subtract r naught from vector p. So p minus r naught is, so that's 985 minus 4, -2, 3. I get 5, 10, 2. Okay, and then now I have that. I want to take the cross product of v and that difference vector that I found. Okay, so v cross p minus r naught. Vector v is 1, -5, -2. Cross with p minus r naught, that's 5, 10, 2. Use the determinant as a mnemonic device to help you take that cross product. So first vector first, 1, -5, -2. And second vector second, 5, 10, 2. I'm going to take this real quick here. So first component, the I component, I get -10 minus -20. So -10 plus 20, that's 10. So that would be my first component, my I component, 10 times I. Okay, J component, I get 2 minus -10. So 2 plus 10 is 12. So 12J, and that's the second component. So I swap the sign, right? Plus, minus. The last component, K, that'll be a plus. 10 minus -25. So that would be 10 plus 25, that's 35. Okay, 35K. So that gives me the vector 10, -12, 35. Okay, that's my cross product on top. I'm still not done with that top, though. I want the norm of that. The norm of v cross p minus r naught is, so let's see, v cross p minus r naught, that's this thing we just got, so that's the norm of 10, -12, 35. So square root of 10 squared plus -12 squared plus 35 squared. And we're starting to deal with pretty big numbers here. Okay, 10 and 12 we could do pretty easily. 35, that's a little bit harder to do in our head. So now might be a good time to pull up a calculator. So I've got my calculator right here. 10 squared plus -12 squared plus 35 squared is 1469. So I get square root of 1469. I'm going to leave it as a square root for now. I can plug it into the calculator later to simplify. I'm going to leave it like that for now. Okay, so that's my numerator. And now I'm going to divide by norm of v. So I need to calculate that. And once I take those two and divide them, that'll give me my d, right? That will give me my distance. So let's take norm of v. Norm of vector v is, where'd it go? 1, -5, -2. So that's norm of the vector 1, -5, -2. That's 1 squared plus -5 squared plus -2 squared. It's 1 plus 25 plus 4 is 30. So I get square root of 30. And so put it all together. I have square root of 1469 on top, square root of 30 on the bottom. If I divide those, that will give me the distance I'm looking for. Okay, so distance d, all I'm doing is I'm plugging into the formula we derived. Okay. By the way, this is not a formula you should memorize. I'm much more interested that you understand how we got it than that you understand how to plug into it. Okay? Plugging into it is fairly straightforward. But hopefully you understand where the formula came from. Okay, so the numerator we just calculated, that's 1469. Denominator, square root of 30. And now that's calculator work again. Okay, so let's plug that, get that calculator again. Move to the other side. Square root of 1469 divided by 30, and I get 6.9976. 6.9976. That is the distance from the point to the line. Next, let's talk about planes in R3. Planes in three-dimensional space. What we would like to do is we would like to derive an equation that describes planes generally in three-dimensional space. How can we do that? Let's think about this. Let's kind of draw a rough outline of a plane here. Remember, a plane is just an infinitely long, infinitely wide flat surface, right? So here I'm drawing it as an illustration with these edges. It really doesn't have these edges, right? It goes infinitely far in every direction. But I can't draw things infinitely far in every direction, so I draw edges, right? For simplicity, let's assume this plane passes through the origin. Later on, we will expand our understanding of planes to think about planes not passing through the origin. But for now, the main idea will be a little bit easier to grasp if we think about the plane passing through the origin. What I want is an equation that is true for all the points in the plane and only the points in the plane. Okay? So if I have some point in the plane, maybe this point here, okay? Maybe this is point x, y, z. I want an equation that is true for only the x, y's, and z's in the plane. So again, we're going to think about this using vector math. So instead of thinking about this as a point, I'm going to think about this as the vector pointing to the point x, y, z. And that would be the vector x, y, z. Right? Let's give it a vector name to keep it simple. This is r. Now I want to emphasize this is just a representative point. Think about this as that it could be any point in the plane. I've drawn it here, but I could have drawn it over here or over here. The idea here is the x, y, and z are variables, and I want an equation so that everything that I could plug into x, y, and z that would be a point in the plane, that the equation would be true for that choice of x, y, and z. Okay? So there are lots of vectors in this plane, right? I've drawn one, but there are lots of them that I could draw. There are lots of directions I could go. What do all these vectors have in common? They're all going off in different directions. It turns out what they have in common is not which directions they do go, but which direction they don't go. All of these vectors are going off in different directions, but they are not going off in this direction. Okay, and that's what they have in common. This vector here is orthogonal to the plane, meets the plane at a right angle. We call this the normal vector. I'm going to use coordinates A, B, and C for now to describe this normal vector. Okay? So we say this is the normal to the plane. Be careful here. Don't confuse normal with the norm of a vector or normalizing a vector. They all sound pretty similar. They're all completely different. The norm of a vector is the operation we do when we find the length of a vector. Normalizing a vector is turning a vector into a unit vector. The normal vector to a plane is a vector orthogonal to the plane. Okay, and notice, by the way, there's lots of choices here. I've drawn one example, but I could have made it longer or shorter, flipped the direction entirely. As long as it is orthogonal to the plane, it would be a vector normal to the plane. It would be a normal vector. Okay, so there's lots of choices I could make here. So now, what do all these vectors in the plane have in common? Well, they are, since they're in the plane, they're also orthogonal to the normal vector, right? What do we know about vectors that are orthogonal? The dot product of two orthogonal vectors is always 0. And that happens only when the vectors are orthogonal. So if I take the normal vector in the plane, and I take the dot product with the vector here, vector r, which has components x, y, z, that should be 0. Okay, and if I plug in the components, that's my normal vector is a, b, c, dotted with vector r, which is the vector with my variables x, y, z. I get 0. If I actually take the dot product, I get ax plus by plus cz equals 0. Okay, that is the formula for a plane that goes through the origin with a normal given by a, b, c. Any x, y, z that I plug in here and that the equation is true, that x, y, z would be in the plane because it is orthogonal to the normal vector. Okay? So simple enough. Let's extend the idea now to work with a plane that is not, that does not go through the origin. Okay? What if I have some other plane? Here. It doesn't go through the origin. Maybe the origin's down here. Okay, here's our origin. But it does go through some other point. We need to know some point it goes through. And then what we want to do is we want to say for any point here, x, y, z, we want to see if this point is in the plane. We're going to use pretty much the same strategy. Okay, we are going to grab a vector that lies in the plane. But now notice it wouldn't just be x, y, z, right? Wouldn't be that. We can find the vector by doing end minus start. So this would be, I want to end up at the point x, y, z. Those are my variables. And I want to subtract where I start off. X naught, y naught, z naught. Okay. Now, this vector here, because it lies in the plane, if I take any vector normal to the plane, any vector normal to the plane, the dot product of this vector normal to the plane and this vector that lies in the plane would be 0, right? So the normal vector dotted with, and let's give these guys names here. Let's say this is still R. Okay, so this is, think about this point as vector R. Okay, that's the vector pointing to it if you want to get technical. Okay, and then this point here we'll call R naught. That's the point we know is in the plane. And so this right here, this would be R minus R naught. So the normal vector dotted with a vector, any vector in the plane is equal to 0. And again, I could do this for any vector in the plane, right? Any point in the plane, I could think about the vector pointing from the point I know to the xyz that I'm trying to reach. Okay, and that vector would be the xyz I'm trying to reach, the R, minus the point I know, the R naught, right? And minus start. Okay, let's plug in. My normal vector is ABC. I'm going to take the dot product of that with vector R. Those are my variables. Vector R is my variables, x, y, z. Those are my unknowns. I know what ABC is. I have to plug in concrete values for ABC. And I know what R naught is. That would be x naught, y naught, z naught. That is a point in the plane. Okay, the only variables here are the x, y, z. All right. So this is the normal to the plane. This is a point in the plane. And I want to emphasize that any normal to the plane will work here. Any point in the plane will work here. Okay, so don't get hung up on which one to choose. Any vector that is normal to the plane will work here. Any point that's in the plane will work here. Okay, the x, y, and z are the variables. Any x, y, z for which the equation is true would be a point in the plane. All right, let's actually do the vector subtraction, the dot product, just so we could see what we get and find the general formula here. So if I do the vector subtraction, I get x minus x naught, y minus y naught, z minus z naught equals 0. Do the dot product, multiply corresponding components. I get a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. This is one of the common equations that we usually use to represent the equation of a plane. Okay, if you ever see anything like this, you're dealing with a plane. Notice how easy it is to recognize the normal vector to the plane. It's just the coefficients of x, y, and z, right? Now, sometimes what we also do is we distribute the a, b, and c. So I get ax minus ax naught plus by minus by naught plus cz minus cz naught equals 0. Okay, I'm going to combine this, this, and this. These are just numbers, right? Ax naught, by naught, cz naught. These are all just numbers. I could add them together and I'd get a different number. I'm going to call it d. So ax plus by plus cz minus d equals 0. And that d is just this and this and this put together. And if I move that d to the other side, I get ax plus by plus cz equals d. This is another common way we represent the equation of a plane. Both are correct, right? Both represent the plane. In both, again, it's real easy to identify the normal vector. Okay, ABC, the coefficients of x, y, z, that's your normal vector. Same thing here. ABC, coefficients of x, y, z, that's your normal vector. I like this equation personally a little bit more because I can see more information about the plane right away. In this form right here, I can also see that x naught, y naught, z naught would be a point in the plane. In this form down here, I don't have that same information readily available. Okay? Even though it communicates the same information, it's a little harder to find, right? Both are acceptable. You will see both formulas in this class for the equation of a plane. So let's take a look at an example. We want to find the equation of the plane containing a particular point and parallel to another plane. All right, so what do we need? If we want to find the equation of a plane, what do we need? Well, the formula for a plane, and I showed you a few different ones, but this is the one I like best because I think it communicates the most information. The equation of a plane is the normal vector to the plane dotted with a vector parallel to the plane equals 0, right? The normal to the plane and any vector in the plane are orthogonal to each other, okay? So we need two things. We need the plane normal, and we need a point in the plane. If we have these two things, then we can construct the equation to the plane. This one right here is just our variable vector, x, y, z. Okay? So we need the plane normal, we need a point in the plane. And we already got the point in the plane, right? There we go. We could use another point if we did the work and found another point, but this is right there and it's ready to go, so that's the easiest one to use, okay? So that's going to be our point in the plane r naught, all right? Now, how do we find a plane normal? Well, the other piece of information that we have is that the plane we're looking for is parallel to this other plane, okay? And if I have two parallel planes, what does that mean? So I get something like this. Okay, so I have these two parallel planes. Now, the first plane, I could look at this and I can easily recognize the normal to the plane because I can see the coefficients in front of the x, the y, and the z. Okay, so the normal to this first plane, I can find. But because the planes are parallel, if this normal vector is orthogonal to the first plane, it would also be orthogonal to the second plane. Too long. Okay, it'd be orthogonal to both planes. So two parallel planes, their normal vectors are the same. The normal vector for one would be a normal vector for the other. Okay, so let's find the normal vector for this plane. The normal vector, remember, would just be the coefficients of the x, y, and z variables. So my normal vector would be 2, -5, 8. And with that, I have everything I need for the equation of a plane. Now just plug in. Okay, so I'm going to plug in my normal vector 2, -5, 8, dotted with r is my variable vector, that's x, y, z, minus a point in the plane, and I have one right there, -4, 7, -8. Okay, and if I do the subtraction and take the dot product, I would get 2x minus -4, x plus 4, minus 5 times y minus 7 plus 8 times z plus 8 equals 0. And I'd probably leave it there. Let's take a look at another example. Here we want to find the equation of a plane through 3 points, right? So we have a plane, and all we know about this plane is that there are 3 points that lie in the plane. As long as those points are not collinear, that they don't lie in a straight line, 3 points determines a plane. Okay? If they lie in a straight line, then there are lots of planes that could rotate around that line, right? If they're not in a straight line, there's only one plane that could go through all 3 points. All right, so how do we find the equation of a plane? Well, what's the equation of a plane? What do we need to know? We need to know 2 things. We need to know a vector normal to the plane and a point in the plane. Now this one's covered. We've got it covered over and over again, right? Because we have 1, 2, 3 points in the plane. Any of them will work for our choice for R0. This could be any point in the plane. Okay? What we need is a vector normal to the plane. That's usually the trickiest part. Okay? So if we take a look at this problem, how are we going to find that normal vector? Well, what I could do with these points is I could find 2 vectors parallel to the plane by subtraction, right? N minus start. Once I have those 2 vectors, what can I do? Well, I want a normal vector of the plane, which means I want a vector that is normal or orthogonal to both of these vectors. Okay? How can I find a vector that's orthogonal to 2 other vectors? Cross product. So if I could find 2 vectors here, I could find this by taking the cross of those 2 vectors. Cross product gives me a vector orthogonal to the original 2. Okay, so that's our strategy. We're going to find 2 vectors in the plane using subtraction, and then take their cross product to find the normal vector. All right, so we're going to call our 2 vectors u and v, as I've drawn here. Now, which ones do I subtract? Doesn't matter. Okay, if I subtract this from this, or this from this, or this from this, no matter how I do it, I will get a vector parallel to the plane because these are all points in the plane, right? So whether I do get this vector, or this vector, or this vector, it doesn't matter. They're all going to be parallel to the plane. So what I just need to make sure I use 2 different sets of points. Okay? So for this first one, I'll use the first 2 points. So -4, -2, -8, minus -5, 4, -3. And that gives me -4 minus -5 is 1, -2 minus 4 is -6, -8 minus -3 is -5. So that's my first vector. And then vector v, same thing, but I want to make sure I use 2 different points. I can't use these 2 points the same. I definitely don't want to take this and subtract that, for example. I need a vector pointing in a totally different direction, but still in the plane. So I need 2 different points. So I could use this one and this one, or I could use this one and this one. Okay? I think in this case, I'll use my last 2. So -5, 4, -3, minus -7, -4, -1. So this will be the vector pointing from this point to this point. And I get 2, 4 minus -4 is 8, and -3 minus -1 is -2. Okay, so I've got 2 vectors parallel to the plane, two vectors in the plane. Now let's take the cross product, and that will give me a vector that is orthogonal to both these vectors, and therefore also a vector orthogonal to the plane, a vector normal to the plane. Okay, so my normal vector, I'll take u cross v. And by the way, I could have also taken v cross u. We've talked about this before. There are lots of possible answers for the normal vector because there's lots of possible ways that I can get a vector orthogonal to this plane. I could go shorter, I could go the other direction, right? But they'll all be scalar multiples of each other. Okay, let's take this cross product. Get my matrix ready. I, j, k. Second row will be u, 1, -6, -5. Third row is v, 2, 8, -2. We've done cross products for a little bit now, so I'm going to move kind of fast here. For I get 12 minus -40. 12 minus -40, that's 12 plus 40, that's 52. Okay. For j, I get -2 minus -10. So -2 plus 10 is 8. And since it is the j component, I swap signs, right? Remember, you swap signs. Plus, minus, plus, the sign you put in front. Okay. And then for the k component, third component, 8 minus -12. So that's 8 plus 12, that's 20. Okay, there's my normal vector. That's the last piece I needed. Okay, so now the formula is normal vector dot variable vector minus a point in the plane equals 0. Plug in, a normal vector is 52, -8, 20. It's not the only normal vector, but any normal vector will work. Variable vector XYZ, and then the point in the plane R0. Any one of these points will work. I could choose any one I want. I'll just choose the first one, -4, -2, -8. Okay, so technically this is a correct answer, but this is not what you would want to put into your homework. It would not be marked correct. In fact, it wouldn't even recognize this. So we do have to do the vector arithmetic to finish this up. So if I do the vector subtraction and take the dot product, I would get 52 x plus 4 minus 8 y plus 2 plus 20 z plus 8 equals 0. And that would be my final answer. That is the equation of the plane that passes through these 3 points. In this example, we want to find the point of intersection between a plane and a line in 3-dimensional space. So first off, I want to point out that if given a plane and a line, there's no guarantee that we will have a point of intersection, right? I could have a situation like this, where I have a plane and then above it, never intersecting, I have a line. Okay, just hovering above it. Most of the time that doesn't happen. Most of the time the plane and the line do intersect. In this particular problem, the problem is implying that the plane and the line intersect, so we can go with that assumption. Okay, we should expect an answer here. Even if they weren't intersecting and we needed to test it, we would use this same approach. Okay, so how do we approach this? Well, I know every point on the line has this structure. Okay, every point on the line can be written this way for some value of t. All right, which means if r of t is x of t, y of t, z of t, then that means x would be, if I do the vector arithmetic, I get 2t minus 2 I get t plus 1, and I get negative 6t plus 2. Okay? So I want to make sure my x, y, and z are equal to this for some value of t. That will make sure that the point is on the line. But also I want to make sure my x, y, and z satisfy this equation. So what I'm going to do is I'm going to plug in the x, y, and z I need here, and I'm going to plug it into the x, y, and z that I need to satisfy this equation. Okay? So x would be 2t minus 2 minus 4 times y. Y is t plus 1. And then plus 4z, where z is 6t plus 2. Negative 6t plus 2. And on the other side, negative 24. And if I can solve for t, that will tell me where on the line I am intersecting the plane. Okay? So this is just one equation, one variable. This is now, algebra 1 problem. So just distribute. I get 12t minus 12 minus 4t minus 4 minus 24t plus 8 equals negative 24. Combine like terms on the left-hand side of the equation. 12t minus 4t is 8t. Minus 24t is negative 16t. And the terms without t's, negative 12 minus 4 is negative 16, plus 8 is negative 8. Okay. Add 8 both sides. I get negative 16t equals negative 16, which means t is going to be equal to 1. Right? So that tells me that this line and plane definitely intersect because I got an answer here. Okay, there is a value of t so that when t is equal to 1, that point also satisfies the equation of the plane. Okay, what I don't know yet is what is the point. I know that it happens at t equals 1, but what point is it at t equals 1? So to get my final answer, I need to plug that value of t back into the equation of a line, and that will tell me the actual point of intersection. So I want to find r of 1. And so that's what? 2, 1, negative 6. 2, 1, negative 6. I'm just copying down the equation of the plane, and then I plug in the value of t I found. Okay, 2, 1, negative 6 times the t, which we found, the t where the line and the plane intersect is at t equals 1. And then I plus negative 2, 1, 2. So if I add these together, I get 2 plus negative 2, that's 0. I get 1 plus 1, that's 2. And I get negative 6 plus 2, that's negative 4. Okay, so the point of intersection is 0, 2, negative 4. That is the point that lies both on the line and in the plane. And you can check, we got this by plugging in 1, so we know it lies on the line. And if you plug 0, 2, negative 4 in here, you will find that we also satisfy the equation of the plane. For this example, we want to find the equation of the line where two planes intersect. So first off, I want you to understand that if two planes intersect, it has to form a line, right? In 3 dimensions, there's only a couple possibilities, 3 possibilities for how two planes can behave, right? Either the planes are parallel, like in this picture, or the two equations really represent the same plane. or the two planes intersect. Just draw the whole thing. And notice if they intersect, it has to form a line. And in 3 dimensions, these are the only 3 possibilities. Either parallel planes, or equal planes, or intersecting planes. Because of how the equation is phrased, we can assume that this is the case that we're dealing with here, that our 2 planes are going to intersect and are going to form a line, okay? If these 2 things happen, notice that the normal vectors for both planes would have to be scalar multiples of each other, right? The normals would point the same direction. They just might have different lengths or maybe be flipped around. Okay. So we know what's going on. How do we actually find the line of intersection? So we know these 2 planes, where they intersect, the x, y, and z values for these 2 planes are going to satisfy both equations at the same time. So the first equation would be true for that x, y, and z, and where they intersect, if you plug in a point of an x, y, z for the point of intersection into the second equation, it'll also be true, right? So what we get is a system of equations. We want all the x, y, z points that satisfy both these equations at the same time. Okay, so what we want to do is we want to get a little bit more information about how both these equations can be satisfied at the same time. We want to work to solve the system. All right. So the easiest approach to this is to solve the system by elimination, to get rid of one of the variables by elimination. Now I could get rid of any one of these variables. It doesn't matter which one. Because I have a choice then, I should try to choose the easiest option. In this case, to me, that looks like the x, because I'd only have to multiply this equation by -2, so that when I add the 2 equations, the x term would go away. Right? For comparison, for the y, I'd have to multiply by the second equation by 7. That's still pretty easy, right? But it's a bigger number. And smaller numbers are easier to work with. Same thing for the z. I just multiply the second equation by -3. Still easy, but -3 is bigger than -2. So if I can use smaller numbers, that makes my life easier. All right? So I'm going to multiply this equation by -2. Both sides. So my first equation stays the same. -6x minus 7y plus 9z equals -3. My second equation, everything's multiplied by -2, so I get 6x minus 2y minus 6z equals -18. You add these together, the x's canceled. That's what we expected. We expected to get rid of that. That eliminates one of our variables. And I get -9y plus 3z equals -21. Okay. And now I've reduced the system to 2 equations with 3 variables into one equation with 2 variables. Any y and z that satisfy this equation can be turned into a point that makes both equations true. Okay. Before I use this, though, I do notice I could simplify this equation a little bit. Always a good idea to see if you could do that. In this case, I could divide everything by 3. Right? So if I multiply both sides by 1/3, then I get negative 3y plus z equals negative 7. Again, smaller numbers, easier to work with, so get them when you can get them. Okay? Now, it's asking for the parametric equation for the line. So that means like the vector form of a line. Okay? We want something of the form r of t equals some point on the line plus t times a direction vector. Okay? So I need both of these things in order to get the equation of the line that I want. Now, there are different ways that we can do this. The way I think is the most straightforward is just solve the system for two and get two different solutions, two different points on the line. Then I'll have 2 points on the line. That's more than I need for that. And I could use those 2 points to find a direction vector. Okay? Again, it's not the only way I could solve this problem, but I think it's the most straightforward and it's the easiest. All right? So I just need 2 solutions. I'm going to start by getting 2 solutions to this equation. Notice if I get a y and z that solve this equation, that's not quite the whole point, right? I will also need to go back to my original equations up here, plug in the y and z to one of them, and get the remaining x variable. Okay? So, which y and z should I choose? I'm going to start by choosing y equals 0. Seems nice and easy. Okay? If you can choose variables that'll make your life easy, do so. Sometimes it's unavoidable. You're going to have some nasty expressions. Okay? But again, if you've got a choice, try to choose an easy choice. So I'm going to choose y equals 0. If I plug that into this equation here, that gives me z equals negative 7. So I've got a y and a z. Now I need to find the x, so I need to plug into one of my original equations. Doesn't matter which one, and since it doesn't matter, try to pick the easiest one. In this case, the second equation looks a little easier to me, so I'll plug into negative 3x plus y plus 3z equals 9. So let me just write that equation down. Negative 3x plus y plus 3z equals 9. Make sure I got it right. Yes, okay. Plug these guys in. So I'm going to plug y equals 0 in. I'm going to plug in z equals negative 7. And I get negative 3x plus 0 plus 3 times negative 7 equals 9. That gives me negative 3x minus 21 equals 9. If I add the 21 to the other side, I get 21 plus 9, that's 30. And so x must be negative 10. And so I have 1 point. X is negative 10, y is 0, z is negative 7. That is 1 point that lies on this line of intersection. Okay? And you can check. That point will satisfy both equations. I made sure the y and the z satisfied the combined equation that I got by combining the 2 equations together. Okay, and once that happened, once I choose a y and a z, there's really only one choice for x in each case, right? So the x has to be the same. Okay, I've got 1 point. I need another point. 2 points determine a line, right? So I need 1 more point. So I need to have 1 more y and z solution here. Again, there's lots of options. I could make z equal to 0, and then y would be, what, 7/3? But 7/3 is a nasty fraction. If I can avoid that, I want to. I may not always be able to, but in this case, I can. I can choose, I see pretty simply, if I choose y equals 2, then I can get negative 6 plus z. Let me actually plug it in so you can see what I'm doing. Negative 3 times the 2 for the y plus z equals negative 7. So that means negative 6 plus z equals negative 7, and I can just choose z to be negative 1. Okay, that is another solution to this, which doesn't require any fractions. Now plug that y and the z into the equation. Negative 3x plus y plus 3z equals 9. Again, I could choose this equation or the other equation for the other point. Either way will work because I've already chosen a y and a z that lies on the line of intersection. And so there's x is no longer free to choose. Okay, x is predetermined by my choice of y and z. So negative 3x plus 2 for the y plus 3 times negative 1 for the z has to be equal to 9. So just solve for the x. 2 minus 3 is negative 1. Add 1 over, negative 3x equals 10. I get x equals negative 10 thirds. So x is a fraction. It is what it is. I couldn't avoid it. Okay, the point that I get is negative 10 thirds for the x, 2 for the y, and negative 1 for the z. So 2, negative 1. Okay, I have everything I need to find the equation of the line. I need a point on the line. I've got 2 of them. And I need a direction vector. So I can find a direction vector by subtracting the points. If I subtract the points, it doesn't matter which I subtract from which, that will give me a vector that goes from one point and ends at the other point. That will point in the direction of the line, right? So I think I'll just do negative 10, 0, negative 7 minus negative 10 thirds to negative 1. Okay, the first one's the trickiest, negative 10 minus negative 10 thirds. You need a common denominator. Negative 10 is the same as negative 30 thirds. Okay, so negative 30 thirds minus negative 10 thirds, that means negative 30 thirds plus 10 thirds, is going to be negative 20 thirds. Second component, 0 minus 2 is negative 2. Third component, negative 7 minus negative 1 is negative 6. And that gives me my direction vector. And put that together, I got my answer. Okay? My final answer, the line of intersection, is a point on the line. I could choose either of these points. This one looks easier, right? No fractions in that one, so that's the one I will use in my formula. Negative 10, 0, negative 7. Plus t times the direction vector, which I calculated here. Negative 20 thirds, negative 2, negative 6. And that is an equation that describes the line of intersection. Okay. By the way, if you wanted to make this a little easier, remember that any scalar multiple of the direction vector also points in the same direction, right? So if you wanted to, you could multiply this by 3. And that would give you a slightly different vector without the fractions. It'd give you what? Negative 20, negative 6, negative 18. Okay, that would also work as a equation of the line of intersection because this vector will be pointing in the same direction. And all I care about is that I get a direction vector pointing in the direction of the line. Okay? For this problem, we want to find the acute angle between two intersecting planes. So we're going to have two planes. Okay, there's plane 1. And here's plane 2. And they're going to intersect. Okay? Okay, so we have our two intersecting planes. How do we find the angle between them? So first off, notice that there are two possible angles we could measure. We could measure this angle, or we could measure this angle. The instructions say the acute angle. So remember the acute angle? An angle is acute if it's less than 90 degrees. So together, these two form 180 degrees, right? So one will be more than 90, one will be less than 90. We want the smaller one. All right, so just keep that in mind. So how do we actually go about doing it? Well, these two planes have two normals. There's the normal to the one plane. Here's the normal to the other plane. Maybe draw it a little lower. Okay, what do we notice about the two normals? Well, the angle of intersection between the planes matches the angle of intersection between these two normal vectors. Okay, and so instead of finding the angle of intersection between the planes directly, we're going to find the angle of intersection between the normal vectors, and it'll be the same. Okay, so that's our strategy. So we can easily find the normal vectors for the two planes. For the first vector here, the normal vector, just take the coefficients of the variables. I get -2, -1, 5. Right? 2, -1, 5. And for the second vector, the coefficients give me the components of the normal vector, so I get 3, -4, -1. And I know that the dot product of the normal vectors will be equal to the norms of the normal vectors times cosine of the angle between them. And it's that theta that I want, that angle between them. Okay, so let's find the dot product first. So multiply corresponding components. So first component times first component plus second component times second component plus third component times third component on the left side. On the right side, I want the norms, so let's calculate those. So I get first component squared plus second component squared plus third component squared, so that's my first normal vector. And then square root of, for my second normal vector, I get 3 squared plus -4 squared plus -1 squared times cosine of the angle between them. So let's do the arithmetic real fast. I have -6 plus 4 is -2 minus 5 is -7. And on the right side, under the first root, I get 4 plus 1 is 5 plus 25 is 30. So square root of 30. And under the other root, I get 9 plus 16 plus 1. That is 26. And so cosine of theta, if I isolate that cosine of theta, I get -7 over the square root of 30 times 26. Whatever that is, that's calculator work. It's a little bit too big that I don't want to do that in my head. Could, but I don't want to. And then I'm really interested in theta, right? Not cosine of theta. So find the inverse cosine of all of this, and that will give me what I want. That will give me the theta. All right? Do note that the problem is asking for the angle in degrees. So when we plug this into the calculator, we need to make sure that it's giving us the answer in degrees. Okay? But this is now calculator work. So let's pull over our calculator. Let me move this to the side so I could put my calculator over here and we're not missing anything. Okay. And we have our cosine of -7 divided by square root of 30 times 26. I am in degree mode, and so I get 104.5153995 degrees. Okay? Theta equals 104. And when I write it down here, I'll round to maybe the second decimal point. When you put this into the problem application, again, I recommend don't try rounding. Just put the full answer in. You can copy and paste it. Okay? So 104.52 degrees. The problem is that isn't an acute angle. This is an angle that's bigger than 90 degrees. So we calculated the wrong angle. To calculate the acute angle, we need to subtract this from 180, right? Remember, together, let's get the right color here. Together, these two angles form 180 degrees. I've calculated one angle. It's too big. So I can find the other angle because the angle that I calculated, we'll call it theta, plus the alpha that I want is equal to 180 degrees. So the alpha that I want, I just take 180 and subtract 104.52 degrees. Okay, so let's plug that into my calculator. So I'm going to do 180 degrees minus, and then I want the previous answer, this number that I just calculated. So I could copy and paste it, or I could just press the answer button and it will plug in the previous answer for me. And so the acute angle between the two planes is 75.48 degrees, rounded to the second decimal. 75.48 degrees. Let's do one more example. Here we want to find the distance from a point to a plane. Okay, so how do we go about doing that? We did something similar with finding the distance from a line to a point. So let's see how it works with finding the distance from a plane to a point. Okay. So as with finding a distance from a point to a line, what we want to do is we want to find the orthogonal distance. Okay, the direct path from the point to the plane. Now, we don't know what this point is. Okay, we don't know the nearest point on the plane to the point that we're interested in. So how do we go about finding this? Well, let's think about what we do know. We have the equation of a plane, so we can pretty easily find a point that lies on the plane. Okay, we can find a point on the plane. Any x, y, z that makes the equation true is a point on the plane. Okay, and I can calculate the vector that points from the point on the plane to the point I'm interested in. Okay, and what else do I know? I know I can easily find from the equation, just looking at it, I could find the normal to the plane. Okay, what I want is this distance here. Okay, or this distance here. It's the same distance, right? And this distance here is just the component of this vector on to the normal vector. And that's starting to sound an awful lot like a dot product. Okay, remember in particular that if I want the component of one vector onto another vector, if I treat this vector as a unit vector, if I change it into a unit vector pointing the same direction, it will spit out the component for me. Okay, so that's my goal. That's my strategy. So I'm going to need a point on the plane, and I'm going to need the normal vector to the plane to make this work. Okay, so a point on the plane, I'll call it R naught. Any point will work. Okay, so I just need an x, y, z that makes this equation true. I see right away that I can choose x to be 0. There's no, it doesn't say anything about x. So I could choose x to be anything. 0 is obviously the easiest, right? Choose x to be 0, y to be 9, and z to be 0. Okay, very clearly that is a solution to this, but you can choose any solution that works. Okay, any solution that makes the equation true gives you a point on the line, right? So that will be the point here that lies on the plane that we're going to choose. The normal to the plane. Well, I don't have an x variable here, so I could think about this as 0x minus 4y minus 3z equals -36. And so the coefficient in front of x would be 0. So 0, and then the coefficient in front of y is -4, the coefficient in front of z is -3, and that is a vector normal to the plane. Okay? Now, the easiest approach here is I want the component here. So I'm going to need this normal vector to be a unit vector. I want a vector that points in the same direction but is a unit vector. So let's go ahead and grab that. So I'm going to normalize the normal vector by dividing by its norm. Okay. The norm is square root of -4 squared plus -3 squared. Notice I didn't bother writing the 0. It's kind of boring. 0, -4, -3 here. Okay. -4 squared is 16, -3 squared is 9, 16 plus 9 is 25, square root of 25 is 5. So I get, right down here, 0, -4, -3 divided by 5. And if I multiply that 1/5 through, I get 0, -4/5, -3/5. Okay, so that is a unit vector pointing in the same direction as the normal vector. All right, and then the other piece I need is I need the vector pointing from the point in the plane to the point I'm trying to find the distance to. Okay, let's call this vector V, just because I don't have a better name for it. Okay, so n minus start, let's end up at the point I'm finding the distance to. So that's -4, 8, -9, minus the vector, the point I'm starting at, 0, 9, 0. Okay, again, any point here will work. Any point here will work. So if you chose a different point, you can still get the correct answer at the end. Okay, so if I do the calculation here, I get -4, -1, and -9. Okay, and so I want the component of V onto n. I've changed n into a unit vector by normalizing it. And so if I take the dot product of a vector with a unit vector, it will tell me the component of the vector in the direction of the unit vector. Very important property of the dot product that we will see many times. The dot product of a vector with a unit vector tells us the component of this vector in this direction. Now, the way I've drawn it, it would be a positive component. But if the normal were pointing the other direction, if it were pointing this direction, then the component it spits out would be a negative value because it would be going in the opposite direction of the vector we're taking the dot product with. Okay? In this case, we really just care about the length of this, not the direction, not whether it's moving in the same direction of this normal vector or in the opposite direction. So because we just care about the length, we're going to take the absolute value so we don't have to worry about the sign. Okay? This is going to give us, this is the formula for the distance from the plane to the point. Okay? So now I just have to take a dot product and take the absolute value of it. So let's plug in. Vector V is -4, -1, and -9. I've already normalized the normal vector, and I found it to be 0, -4/5, -3/5. If I take the dot product, first component times first component plus second component times second component plus third component times third component. -4 times 0 is 0, that just goes away. -1 times -4/5 is +4/5. -9 times -3/5 is +27/5. 4/5 plus 27/5, they already have a common denominator, so I could just add them. I get 31/5. Absolute value of 31/5 is 31/5. So that is the distance from the plane to the point.